When a new AI model drops, the question that matters for most teams is not the leaderboard score. It is whether your stack can run it reliably, what it costs at your traffic scale, and which shortcuts will break in production. Today, we connect that headline to the engineering trade-offs behind the hype. You might think your GPU is just slow, but new interpretability research suggests a darker reality. Your hardware is working twice as hard for nothing. The recent findings from Anthropic reveal a hidden inefficiency built into how standard large language models operate. These models contain specific internal neural pathways dedicated solely to blocking prompts. They act like automatic brakes that engage even when you do not need them blocked. For engineers deploying these systems on dense GPUs, this means your hardware is burning cycles calculating a refusal for every single token, regardless of the prompt's actual intent. The finding forces a hard pivot. Relying on benchmark scores alone ignores these hidden computational dead ends that inflate inference costs by 20 to 40% in real-world scenarios where models are frequently asked to decline requests they were trained to refuse. To understand why this happens, we need to look at what is happening inside the model when it processes your request. Analysis via tools like Obliteratus, a community-driven interpretability toolkit, identifies specific vectors within transformer layers that trigger hard refusal responses. These are internal directions in the neural network responsible for saying no. Crucially, these mechanisms remain active during inference even when the model is performing valid tasks. This creates redundant computation paths that standard dense hardware cannot bypass without retraining or specialized architectural changes. The core conflict lies between sparse activation and dense hardware design. Modern LLMs utilize a concept called sparse activation, where only specific neurons fire for a given token to generate an output. However, current consumer and cloud GPUs like the H100 or A100 are designed as dense matrix multiplication engines. They process the entire batch of potential activations regardless of sparsity, unless explicitly optimized via specialized hardware or quantization techniques that do not yet exist in standard inference stacks. This mismatch means your expensive silicon is forced to calculate everything, even when only a tiny fraction of those calculations results in actual output tokens for you. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This leads us to the specific cost of refusal mechanisms. The research indicates that these safety features act as blunt instruments, activating high-dimensional vectors to block content across all layers simultaneously. When a model is asked a benign question but has been trained with strong safety guardrails, the system still computes the full cost of these internal blocks before determining they are not needed for that specific output. Effectively, you are wasting compute on ghost calculations that never result in user-facing tokens. The hardware must execute dense operations to suppress these vectors, creating a scenario where theoretical performance metrics like flops per second are rarely achieved in practice because the system is fighting its own internal architecture to produce results. Unlike academic benchmarks, which often test on clean datasets without adversarial or refusal-heavy prompts, production environments see high variance. The presence of these internal blocks means that a model's advertised efficiency is an illusion when deployed at scale. Developers are currently selecting models based on benchmark scores such as MMLU or GSM-8K, which measure accuracy but not computational efficiency during inference. If a model has heavy internal refusal mechanisms, its effective cost per token is significantly higher than the manufacturer claims because your GPU is doing work that yields no output value for your business logic. This creates a critical decision heuristic for engineers in 2034 and beyond. You must shift from asking which model scores highest to how sparse are this model's activation patterns for your specific use case. If a model requires dense computation to suppress internal refusal vectors, it may be cheaper and faster to deploy a smaller, less parameter-heavy model with fewer safety constraints than a massive model fighting its own internal architecture. For high-volume inference where cost is critical, the brief suggests evaluating models for what we can call internal friction before deployment. If your goal is pure throughput and not maximum alignment on sensitive topics, bypassing dense hardware reliance by using quantized variance or sparsity-aware architectures becomes a priority over raw parameter count. The statistics paint a stark picture of this inefficiency in action. In studies measuring behavioral shifts within these systems, there was a factor of 3.39 increase in odds for going guaranteed rewards when internal conflicts were present. Furthermore, earnings reduced by a range between 10.7% and 42.9% due to these hidden computational overheads. Over 40% of the total participant pool exhibited this behavioral shift, indicating that almost half of all standard deployments are suffering from unnecessary latency and cost inflation caused by these refusal mechanisms firing unnecessarily. This means interpretability is no longer just research theory. It has become a financial imperative for any team running AI at scale. The future of AI deployment requires looking inside the black box to save compute budgets, rather than treating models as opaque boxes where more parameters always equal better performance. Engineers must now consider how these internal breaks interact with their specific traffic patterns and whether they are paying a premium for safety features that never engage during normal operation. By understanding the mechanics of sparse activation versus dense hardware constraints, you can make informed choices about model selection that directly impact your bottom line. The path forward involves rethinking how we validate models before deployment. Instead of accepting benchmark scores as the sole metric of quality, teams must investigate internal friction and activation sparsity to ensure their infrastructure is not burning cycles on ghost calculations. This shift in perspective allows practitioners to align their engineering decisions with economic reality rather than marketing hype. It turns a complex research finding into a practical rule for survival in an era where compute costs are rising faster than model capabilities can justify the expense of redundant internal processing. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.